Hello everyone and welcome to another topic webinar. Today we will be looking at electron diffraction again. Today's speaker is Emilia Götz. She is our newest application scientist in our Frankfurt office and she's been with us for just over 6 months. I won't take too much of your time, but as usual I'd just like to make some quick announcements. So firstly, if I can get my screen to change, there we go. So we are recording this webinar, so this will be available via our website following the event. And if you're interested in seeing any of our past webinars, there's now quite a large library of those at the URL shown on screen just now. If you would like to know about upcoming events as well, if you go to this link, there's also a link there which tells you upcoming webinars or something like that, which will let you see a list of the latest that have been added to be shown in the future. Okay, during the presentation you can ask questions. Please use the Q&A. You'll be able to see other people's questions, and if something is of particular interest to you, please feel free to upvote it, and then it will float to the top of the questions and we can place a bit more emphasis on those and ask them first. We'll try to answer as many questions as we can, but if we start to run out of time, we may resort to putting some of the answers to the questions online. Please do join our forum if you haven't already. So there's a QR code here which you can use to get to the forum address, or it's written at the top of the screen. We have lots of information on our forum which is useful, things like software how-tos. You can download the software there, some short videos on how to do various things, and it's a nice place where you can communicate directly with each other to get answers to commonly asked questions. Just before we move on to the actual webinar today, I'd like to advertise our next webinar. So our speaker will be Dr. Brandon Mercado at Yale University, and he's going to give us an insight into how he runs his facility at Yale University and his plans there. So that will be on the 25th of July at 3 p.m. GMT, so it's the same time as this webinar. That's 10 a.m. Eastern Time, 9 a.m. Central Time in America. You can use this QR code to get to a sign up page. We haven't got the actual page up and running yet, but this will put you onto a list and you'll automatically be registered when that page is ready. Okay, so without any further ado, I'd like to pass the microphone over to Emilia to give her presentation. So I will stop sharing and allow you to start sharing, Emilia, and take it away when you're ready.
Yes, thank you, Fraser. So I hope you can see my screen now.
Yes.
And I also welcome you to this Rigaku topic webinar. I will talk about three-dimensional electron diffraction with the XtaLAB Synergy-ED today, and specifically about how all of the structures were published with this instrument and technique. So for everyone who's not familiar, I will start with a short introduction about three-dimensional electron diffraction. And as you certainly know, X-ray diffraction gives you access to crystal sizes down to 1 micron. And here you can see the portfolio of instruments of Rigaku Oxford diffraction, all the way from a benchtop instrument to the high-end instrument and even a synchrotron. But there's a certain barrier of 1 micron, and below that it becomes very difficult to get good diffraction signal out of single crystals. And for electrons, a 1 micron crystal is essentially a beam stop because electrons interact many orders of magnitude more strongly with any matter, which means that even with tiny crystals, you can get sufficient signal to solve a crystal structure from a single crystallite the size of a powder grain. Of course, if the crystals get bigger, then electrons will just not pass through, such that electron and X-ray diffraction are actually complementary techniques to give you access to a whole range of crystal sizes from the nanometric regime all the way up to millimeter-sized crystals. In most modern electron diffraction techniques, the measurement scheme is very similar to single crystal X-ray diffraction, where you basically replace X-rays by an electron beam. So you have a crystal which rotates continuously in the beam, and you do a shutterless continuous collection. And even though this technique has been studied as early as the 60s, it was again rediscovered starting in the early 2000s in several groups, more or less independently. And for that reason, it's now known under a lot of different names and abbreviations, which all more or less refer to the same thing. And the most common umbrella terms nowadays are 3D-ED and micro-ED, and I'm going to use those two terms interchangeably. It has by now been applied to pretty much anything that crystallizes, including proteins, but predominantly small molecules, pharmaceuticals, any sort of small organics, really, metal organic frameworks, other porous materials, minerals, etc. And so far, those studies have mostly been conducted in transmission electron microscopes. So you need a research group that is capable of both operating a TEM and having the crystallographic skills to do those measurements in the first place. And there are precious few of these research groups available. Luckily, recently, user-friendly commercial solutions have become available, and that makes this technique accessible to a wider audience of crystallographers. So let me now walk you through a standard 3D-ED experiment on the Synergy-ED. The instrument control, data collection, and finalization are all done in XtaLAB Pro. And after inserting the sample, you first screen for suitable crystals. And when you have found a well-diffracting one, you center it and collect the data. And concurrently, XtaLAB will process the diffraction data, and OLEX or AutoChem will solve and refine the structure similar to our X-ray diffractometers. So let's have a look now at how this is done in practice. Here we have a short video where you can see the XtaLAB user interface, and we will now ramp up the current by turning the beam on and engaging the filament, and this takes about 1 to 2 minutes. And by going to the start and stop buttons and clicking on run visual mode, we should slowly see an image appear on the screen, and the signal should get stronger over time, generating more contrast. And then once our beam is fully on, the first thing we do with a new sample grid is to take a very low magnification image of the entire grid, which is called minimap. And in the minimap window, we can then change the level of contrast with a slider, as well as zoom in and zoom out. Back on the grid, we can then navigate either with a trackball, which is the most familiar thing to the electron microscopists, but we can also directly point and click on the screen, or we can go to a selected position on the minimap. And then the next step, of course, would be to find a suitable grain. So first we will have to look for one, and then when we found one that looks promising, we will bring it to the crosshair, and then we will check if it diffracts by switching to diffraction mode. And if we are happy with the diffraction pattern and the resolution, then we can return back to visual mode. And in the next step, similar to single crystal X-ray diffraction, we center the crystal on the rotation axis of the stage. And this is done by tilting the stage to a certain angle. And we have a visual indicator on the left showing us the current tilt angle, as well as the scale bar, which corresponds to 1 micron. So by using the point and click interface of the mouse wheel, we adjust the Z position of the crystal. And during the rotation, the crystal should always remain within the red circle that is shown in the middle, since this is the size of the selected area aperture and thus the area from which we will get the diffraction information. This means that the area from which we receive the diffraction information is not the field of view that we can see here in visual mode, but it's much smaller and more defined. So once we have figured out the scan range from negative to positive and go as far as we can then set up the data collection. And if we want to start a data collection, we click on the button Start Experiment, and then a new window will open, and we should now add all of the necessary information for the data collection, such as the sample name, chemical formula, exposure time, scan range, scan width. And the data collection time will then be calculated, and based on the input information, and in this case, it lasts around 2 minutes, which is totally normal for an ED experiment. So once we click on Start Experiment, the stage will move to the starting position, which is minus 65 degrees in this case, and then it will start the diffraction experiment. And concurrent to the data collection, we can see on the right-hand side that the data is being processed by XtaLAB Pro. So first it will look for a unit cell, and when it has determined unit cell, data will be integrated and reduced, and then after enough collected data, AutoChem will start. And although this data is not complete at the beginning here, and there are still some not correctly assigned atoms, the crystal structure has already been solved, and it's tyrosine in this case. So here's a comprehensive flow chart summarizing the workflow for a 3D ED experiment. And as shown in the previous video, an actual measurement performed on the XtaLAB Synergy-ED is quite fast and takes only a couple of minutes. The step where you usually spend a lot of time, especially with research sample, is the screening process. So you will probably find crystallites which have poor quality or are amorphous and have different unit cells maybe, or suffer from radiation damage. And this will result in going back and forth from visual mode to diffraction mode and searching for a better grain. And for this, there are some solutions already implemented as automated workflows in XtaLAB Pro. Because the key difference of electron diffraction with respect to X-ray diffraction is the importance of multi-crystal workflows. And the reason for this is quite obvious if you look at the specimen for electron diffraction, which is comprised of not one, but thousands of crystals, which are deposited on the sample grid. And here we can just see a tiny section of the sample grid where we already have dozens of crystals. And those usually vary wildly in quality of diffraction to get out of them. There are also other important aspects, which is the limited completeness you can get out of each crystal, especially if it's in a low symmetry space group. You can have different polymorphs or even mixtures of different compounds or impurities in your sample. And so it becomes really important to screen and also collect from a number of crystals and not only a single one. In XtaLAB Pro, we have a specific tool for managing many crystal data sets, which is called the ED Results Viewer, which allows you to stay on top of collected data for many crystals and allows to list them, filter them, sort them, and one of the most important ones, merge them. So you typically need to merge data sets to achieve sufficient completeness for structure solution, especially for triclinic structures. But even for higher symmetries, merging data sets will often result in higher signal to noise ratio and a better quality of the data set. And it will also mitigate artifacts arising from dynamical diffraction if you still refine them in a kinematical approximation. Finally, if you have extremely radiation sensitive crystals, one strategy to cope with it is to collect only small wedges of reciprocal space from each crystal and then merge them together. Another possibility would, of course, be to use cryotransfer and measure the sample at 100 Kelvin, which can also be done. And in order to keep this process easy and fast, the measurement can be automated. So this is really where the true power of electron diffraction is unleashed, is if you automate your machine and your data processing as much as possible. The Synergy-ED has a feature for that. It's called a queue, which allows you to set up measurements in advance, which will then be run in an unattended way. And some typical use cases are just simple crystal screening, where you would go up to even hundreds of crystals and just take a single short diffraction snapshot to assess whether or not it gives a good quality diffraction pattern. And then after it has gone through the queue, maybe spending an hour on it, you can revisit the crystals that have a good diffraction data for full data collection. Another very important case is crystal mapping. which basically means finding out what compounds you have in your powder in the first place. And you can get a good idea of this by just taking relatively small wedge, let's say over 40 degrees of total collection angle, and by this unambiguously identify the unit cells and assign each grain to a certain compound or polymorph. So you'll know what is actually inside your powder, even if it's a mixture. And of course, you can also queue full data collections, as many as you want, and then have a very long unattended collection queue. And these automations are really being worked on a lot right now in order to improve the ease of use and to decrease the actual instrument time. So now we've arrived at the topic that I want to spend the rest of the webinar talking about, and that is the numerous publications that came and are still coming out of the Synergy-ED. As you can see, we've published quite a few in the past 2.5 years, and I would like to give you an overview of some, if not all of them. So over the next slides, I will try to categorize them in different ways and give respective examples for common or special cases. And for this, we'll always come back to some statistics. And the first one that I want to show you is the timeline of the Synergy-ED publications. You can see that the first paper was already published in November 21, and at the beginning of 23, more and more publications started coming in, with the time in between papers decreasing constantly. So what were those very early publications? Well, the first one was created by our Japanese colleagues from Rigaku about the general handling of the Synergy-ED. The second one from January 22, however, was this one by Pierce et al., which got published in Nature Communications as an editor's highlight. And they used 3D-ED because the crystals were only diffracting very poorly in single crystal X-ray diffraction. With electron diffraction, they managed to solve this pretty large macromolecular structure with a volume of 5,000 square angstrom and a P1 bar symmetry, which you can see here. And over here, the crystals used for structure solution are shown with their respective diffraction patterns. And interestingly, they also tried the structure solution at a synchrotron, and the electron diffraction data led to better results. So you can see that the structure from the synchrotron data was only achieved by using loads of restraints, and even then the PF6- was missing and atoms were basically placed in the expected positions. For electron diffraction data, the structure solution could be performed ab initio, and the PF6- was located. There was barely any help from restraints or constraints. And even though electron diffraction is not famous for its low R values, in this case, the R value was actually lower than the one from synchrotron data. So next, let's have a look at the impact factor of the journals that the papers were published in. We have the majority being in a high one-digit range, and then we have another peak at around 15 to 17, and these are the papers that were published, for example, in Angewandte Chemie or Nature Communications. And all the way back here at 47, we see one paper that recently got published in Science. So let's have a look at that one. This paper by Alexander et al. Is about oxidative photocyclization of alkaloids, and these cytotoxic alkaloids with reactive alkene and heterocyclic residues have a structural complexity which leads to a rich chemistry, but this also makes them difficult to synthesize. And in this paper, a new route to 8 isolates was presented, and the structure of one of those isolates was solved with the Synergy-ED because it was too small for a single crystal X-ray diffraction. And this structure had an R value of 14.9%. So we've already seen in the paper before that the R value was over 20. So why do we have such relatively high R values for electron diffraction? One of the main reasons is that we tend to assume kinematical scattering whereas for electron diffraction, we'd need to apply the dynamical approximation. And through these dynamical effects, the intensity of the diffraction spots are changed to a certain extent, and parameters that are looked at in single crystal X-ray diffraction kind of lose their meaning for electron diffraction. So a 2-digit R value doesn't mean we have bad data or that the structure is wrong. In fact, you can see here that most publications used kinematical refinement only and got R values in the 10 to 20% range for reasonable structure solutions. And a couple of them also refined with the dynamical approximation, which then led to generally lower R values. One of the main reasons, besides lower R values, that speaks for a dynamical refinement is also that in this way, the absolute structure can be determined. And Chrysalis Pro can automatically output a file for dynamical refinement in IANA 2020. And you can use the structure model, which you got from your kinematical refinement in OLEX. And then you can perform a dynamical refinement with IANA 2020 and calculate the fit of the intensities of your experiment to the calculated intensities of the original or inverted structure. And this will give you a so-called Z-score. If you want to know more about how this Z-score is calculated after the dynamical refinement, I recommend this paper by Pautlar et al., where everything is explained. But in short, a Z-score of over 3 sigma has an about 99% probability that said absolute structure is the correct one. So here we have examples to show this. This is an easy test sample, tyrosine again. First, we can see that the R value decreases significantly by about half after applying the dynamical refinement. And here we can see that we have a Z-score of 10 sigma, so it is extremely certain that the L-tyrosine is the correct absolute structure. Even on more complex systems, as clarithromycin, we managed to get a high Z-score. Here we can also see the difference between the R values of the correct and inverted structure, but in some cases, this difference might not be as large. So it's really good to have another value to go by. And here are some more published structures which were refined dynamically to get the absolute configuration. Here we have an iron porphyrin complex, an API, and a fungicidal product. And in all cases, the Z-scores are above 3 sigma. And in the first two cases, it was even sufficient to only refine the scale. And here, atom coordinates and ADPs were refined as well. Another thing that we can have a look at is the resolution. The resolution of most datasets was around 0.8, which makes sense since this is the resolution that is required most of the time. Of course, some structures did not diffract that strongly, so the resolution had to be cut, but still the structure could be solved. And some had a really nice high resolution of around 0.6 angstrom, like this ceramic polymorph published by Kahlenberg et al. And here it could be shown with the help of 3D-ED that a triclinic sodium calcium silicate with a stoichiometry of 1 to 3 to 2 probably does not exist, but it is the gamma phase instead of the material, which differs from the beta phase by the orientation of every other silicon tetrahedra along this chain. And in this case, the crystal that was used for structure solution produced good diffraction signal up to 0.6 angstrom. Another structure with a high resolution of 0.65 angstrom was published in this paper by Xue et al. And in this case, it's not an inorganic one, but actually a MOF, or actually several MOF structures. So this really shows that we can also get high resolution data from these kinds of crystals and not just nicely diffracting inorganic ones. Besides high resolution, it's of course beneficial to also have high completeness. And for electron diffraction, this is harder to achieve with a single crystal than with single crystal X-ray diffraction. because we can only tilt along one axis. So especially for low symmetries, we might not get 100% completeness. And we can see here that low symmetry crystal systems like triclinic and monoclinic make up almost half of the published structures. But what we can do, like I explained before, is merge data sets of different crystals together. And this will increase the completeness and also the redundancy, and it will usually help us get better ADPs in the end. But as you can see, data merging was not necessarily in all cases, and some even got a structure with a relatively low completeness, below 70%. Like this MOF paper from Steinke et al., for example. In their case, just the powder pattern was not enough to find a structure model, and they managed to solve the crystal structure of YCAO34, a MOF with rare earth elements in it, with 3D-ED, although only obtaining a completeness of 66% because of its monoclinic structure. However, the completeness didn't matter that much in this case because they then refined the model on the powder data with the Rietveld algorithm and managed to get a nice refined model out of it that way. So we've already seen some examples on which kinds of materials the Synergy-ED was used, but here's a general overview again. We can see that about half of the structures published were organics, mainly small molecules, and if we also count APIs to that, which I've listed separately in this case, then it's an even bigger part. The second biggest part is MOFs or MOF-like structures, and then we also have a certain amount of inorganics and a small amount of proteins. So let's first have a look at the MOF structures, or at least the ones I haven't talked about already. Electron diffraction is usually pretty beneficial for MOF structure solution because we don't need large crystals to be grown. We can also drop cast the crystals directly from the mother liquor and cryo plunge them before inserting them into the cryo transfer holder so that the possibility of a solvent loss is minimized. And this way, the Synergy-ED was able to help many scientists in solving their MOF structures. And here we can see two examples of Casper Pedersen's group, who now have their own Synergy-ED in Copenhagen since last winter. They solved the structure of a palladium MOF and one with metal carbonyl synthons. And Poschmann et al. Also managed to solve the MOF in their paper about zirconium chalidamates with the Synergy-ED. And these MOFs were also all solved by electron diffraction. The one in the paper by Wang et al. Can be used for carbon hydroxide capture in high humidity. And the other two papers by the working group of Christos Maliakas from Northwestern University, they also just got their own Synergy-ED installed this month, basically. They solved two structures, one zirconium MOF and one copper MOF, which can be used for SO2 capture and inverse propane-propylene separation, respectively. And of course, 3D-ED can also be useful for structures that are similar to MOFs, like COFs, CIFs, or other coordination networks, of which we can see a few examples here. Here, a flexible coordination network, which has a selective sorption of oxygen and nitrous oxide, was analyzed. In this paper by Buddha et al., a COF structure was solved by 3D-ED. In this publication, the structure of a porous nickel-based ZIF was determined, which can act as a heterogeneous catalyst. And in this paper by Yang et al., the structure was a 1D porous letter covalent polymer, which can be used to remove CO2 from an acetylene CO2 mixture to obtain high purity acetylene. But as you have seen in the diagram, we also have applied 3D-ED to several active pharmaceutical compounds. And this one here is a really nice example where a pill from a pharmacy was basically ground up and then dispersed on a grid. And then by using queuing, loads of crystals were tested in an unattended way so that the API could be found among all the other things contained in the pill, most of which were also crystalline, so you wouldn't have been able to differentiate them at first glance. And with these data sets, the absolute structure of the API could be solved with a combination of Chrysalis Pro and Jana 2020, which you've already seen a couple of slides ago. Another interesting thing to look at are the longest axes that have been published with the Synergy-ED so far. We can see that the largest amount is below 30 angstroms, which is mainly due to the amount of small molecules measured, and then in the higher range also MOFs. And then there is a peak at around 57 angstrom, which is clarithromycin. And then we have one all the way back there, which is a protein. And because, of course, this is also possible to do a structure solution of proteins with the Synergy-ED. And we have shown this exemplarily on thaumatin in the paper by Zhuang et al. Of course, the sample preparation is a lot more complicated and time-consuming than for non-protein samples, although there are several methods to be considered and some might require less effort than others. But in this case, we managed to process the collected data to 2.15 angstrom and solve and refine the structure with even some hydrogen atoms observable. These long axes of proteins, or in this case, thaumatin, can be measured on the Synergy-ED because we can go to some pretty long detector distances. In this case, the data was collected at a detector distance of 1.8 meters, while still having a 1.2 angstrom resolution on the detector. But in theory, we could go up to even 3 meters. So there is some space to resolve some even longer axes. And of course, not all of these measurements were performed at room temperature. You can see that a significant part was performed under cryo conditions. And that is because on the one side, the atoms move less at colder temperatures, so the ADPs will generally be better, but also the material will be more stable under vacuum conditions, and the diffraction limit will generally increase. Additionally, solvents or volatile constituents in general can be frozen inside the structure and so be hindered from evaporation in the evacuated instrument column. So let's have a look at a couple of examples for cryo measurements. In this structure, which was published by Kubens et al., we can see a fungicide, which looks like this when measured at room temperature, so with no water in it. But when measured at 100 Kelvin after cryo transfer, we can see that the water stayed in the structure and the structure is actually slightly different as well. So we can prevent the dehydration of the structure with cryotransferring the sample. And another example of this was published by Stola et al., where again, the co-crystallized water was lost at room temperature measurements, but stayed in the co-crystal when doing a cryotransfer and measuring at 100 Kelvin. Interestingly, sometimes the change in the crystal structure is even visible in situ in the instrument, like it was in this paper by Mies et al. About the characterization of new calcium pyransolanato complexes. And here a solvation of the coordination sphere of calcium was seen during the measurements. So first, the structure of the calcium complex with water could be determined, and then an in situ desolvation could be observed where the water was lost from the calcium complex and this structure was formed. But of course, not only pure cryo measurements are possible, you can do variable temperature measurements as well, like in this publication by Kronavita et al. About the spin state of certain iron MOFs. And here, the same grains of the respective MTA and CTA MOF were measured at 173, 233, 293, and 373 Kelvin to observe changes in the structure. And here it could be discovered that these two structures are in a high spin state compared to the low spin state TA structure at room temperature, and that the modification in the MTA and CTA compared to the TA has a significant impact on the void fraction in the structure. So now we come to probably the biggest question for measuring with the Synergy-ED, because why couldn't we just use X-rays? And while for a lot of the samples, the reason was not clearly defined in the publications, the biggest issue, and I guess this also counts for a lot of the undescribed reasons, is that the crystals were simply too small to be measured with single crystal X-ray diffraction. But there were also some other reasons named, like having a second phase included or a bad diffraction quality during X-ray measurements. So let's look at some publications with crystals that were too small. In this paper by Sakamoto and Gacho, a structure of a co-crystal was solved where the crystals were 1 micron in size, but they were very thin platelets only. And in this paper by Klimova et al., potential anti-cancer agents were solved with the Synergy-ED, with crystals being in the size range of only 200 nanometers. In these publications by Pereira et al. And New et al., the crystals were 1 micron size platelets as well, where the thickness just wasn't sufficient for a single crystal X-ray diffraction. But as I said, sometimes it's not the crystal size that brings people to the Synergy-ED. In case of the paper by Stegmann et al., the NMR measurements clearly showed 2 titanium phosphate phases in their material, one of which was unknown. And they tried XRPD first, but because of the presence of the other polymorph, they weren't able to identify the correct structure of the unknown polymorph. And then again, for a single crystal X-ray diffraction, the crystals were too small, which led them to 3D-ED, which worked really nicely to solve the structure of the unknown polymorph. And for this structure by Miano et al., they actually tried single crystal X-ray measurements for a polymorph of this API, but the diffraction spots were elongated and the resolution was not sufficient. And the XRPD pattern did not indicate several phases, but they also weren't able to index it correctly. And after the 3D-ED measurements, they realized that the polymorph they were looking at was actually 2 different polymorphs, which you can see here. And their peaks in the powder pattern simply had a lot of overlap. So now we've gone through almost all of the currently published papers that use the Synergy-ED for structure solution, but I want to show you 3 more because the last ones all were structures that were measured in cooperation with the application labs of Rigaku, be it in Japan, the US, or Germany. But since the Synergy-ED is being sold all around the world now, there are now more and more publications coming up where the customers use their own Synergy-ED. Like this one from Ramana et al., where they solved several crystal structures of tin coordination polymers with the Synergy-ED, or this one from Iketa and Kodairo, where they analyzed the structure of an aluminophosphate, which has an ion exchange ability for alkaline metal ions and a gas absorption ability, or this one from Otsuka et al., where they determined structures of compounds that are possibly usable in treating Alzheimer's disease. So with this, I'm almost at the end of the talk, and I want to end it with a quick conclusion. I guess by now it is well known that 3D-ED allows to solve structures from a single submicron crystal within bare minutes. And despite having very different hardware, the workflow in the Synergy-ED is very similar to single crystal X-ray diffraction. And we've seen that there are all kinds of different structures published already. which will surely increase even more, especially with the continued development of new features for the Synergy-ED. And with cryogenic workflows, allowing to study hydrated, solvated, or radiation-sensitive samples, so that in the end, we can really measure basically any kind of structure as long as the crystals are small enough and are actually crystalline. And if you want to have a look at a specific publication that I mentioned throughout this talk, we do have all of them listed on the Rigaku webpage, so you can look them up there. So with this, I'm at the end of my presentation. If you think you have a sample that could be measured with the Synergy-ED, we do have a measurement service for data collection and structure solution in our application labs. So feel free to contact us. And if there are now any questions, I'm happy to answer them. Although I'm not sure how much help I can be for specific publications, there it's probably best if you ask the authors directly.